Welcome back to Math for Game Developers. Last week we looked at how giving structure to our data by sorting it could make it very fast to look up data in a list by doing a binary search. And this week we're going to use the same example. These are models of our game. We have a fish model, bat model, dog model, and so on. But we're going to add a different structure. We can see how this different structure will give us an even faster time to find the data that we need in our array. And we're going to do that. Okay, let me draw our array here. This is going to be our array, and we're going to make a function called a hash function. Okay. I'm going to call this function h. And the function will accept a string, that being any of the names of these models. And it will output an index, as random of an index as possible. And the index will be the index to this array right here. So if this let's break this array into entries, individual entries, so we can see what's going on here. And this should have 16 entries now, so there will be 0 to 15. But in a real world application, you will have many entries, maybe even like 100,000 entries. And so we're going to say k is the number of entries in the array. And then our hash function will accept one of these strings. So for example, let's say fish. And then it will return a random index in the array. So for example, it might say 5. And then we will put the fish wherever the hash function tells us to put it. So 0, 1, 2, 3, 4, 5. We'll put it here at 5. Fish. And then all of the data for fish will go in this entry right here. So fish goes here. And then we do that again for bat. And we put bat wherever the hash function tells us to put it, which let's say it says here. And then we do the same for dog, and then we put dog here, and then we run horse through the hash function, and horse goes here. And then we run dragon through the hash function, and dragon goes here. The hash function gives us a random index to put it. And so we can see the benefit of this is that, for example, if we want to look up horse, then we just run horse through our hash function. And if our hash function is fast, and we're going to see that we can make a very fast hash function, then we can find where horse is, where the data for horse is, in only the time that it takes to run the hash function. And if we want to add a cat, okay, then we just run cat through the hash function. We see we have many open spaces, so we put cache wherever the hash function says to put it. We put it right here. But there's a drawback. There's a serious drawback with a hash table, which is what this is called. This is now called a hash table. Hash table. And the drawback is that what if our random function says that firefly and bat should go into the same index? That would be a problem. And it's entirely possible because there are only k entries in this hash table. And so and you may have you have an infinite number of names that you can have. You have very many names, but they have to fit inside a hash table of size k. So it's possible that two names could be put into the same index. And so that's called a collision. And collisions are fairly common with hash tables. And there are many strategies on how to deal with collisions. But we're just going to go over a simple one, which is to take the firefly and put it in the very next index. Now the next time you want to go look for firefly, you follow the hash function. It says you should put it in this index, but you see there's a bat already there. And so you go to the next index and you see, well, there's my firefly. It's in the next one. Now this strategy for dealing with collisions has some weaknesses. For example, if bat is removed, then the firefly is not going to know to look at the next one. So we can't do deletes with this strategy. But you can use different strategies for dealing with collisions. And a lot of those are available in a lot of different places on the internet, so I'm not going to cover them. Let's look next at how to implement the hash function. So the hash function accepts this string. And a really simple hash function might be to do a sum. This is the sum symbol of every index of the string. So we say f plus I plus s plus h. Now you're asking me, that's stupid. How can we sum a letter? What does f plus I mean? Well, each letter is represented in the computer by a number. So for example, I just happen to know that the letter F is represented by the number 70, and the letter I is represented by the letter 70, by the number 73. So when we add these letters, what we're adding is 70 plus 73 plus whatever number is used for S plus whatever number is for H. And then the one last step that we have to do is we have to do a mod k, because we make sure we can never overrun the bounds of this array. So if we do a mod k, then that will return for us a number between 0 and k minus 1, which are the valid index entries of our hash table. So this is a pretty good hash function, except that it has a problem. The hash value for dog is going to be the same as the hash value for God. So if we have a God model and a dog model, then they'll go into the same entry. And that'll cause a collision. And we know how to deal with collisions, but we want to avoid them as much as possible. So we can do a really simple change to our hash function to avoid this commutivity problem. This is called commutivity because D plus O plus G, the numbers for them, is the same as the numbers for G plus O plus D, because addition is commutative. So here's what we want to do instead. We're going to do the sum of the letters SI, but now we're going to multiply by I, and then we'll put in our mod k. So here's how that will look. It will be D times 0 plus O times 1 plus G times 2, and that is not equal to D, G times 0 plus O times 1 plus D times 2. You can see here the D gets multiplied by 2, and here the G gets multiplied by 2. So now it will produce different numbers. So that's another improvement to our hash algorithm, but we still have a problem. What if k is a really big number, like 100,000, and these numbers that represent these letters are all really small, 70, 73. When you add them up, even when you're multiplying by this number, you're going to get small numbers. They're going to be below 10,000. And so you're going to get a large part of your hash table that's not used at all. So we're going to fix that problem by taking one more pass at this hash algorithm, which is turning more purple as I go. So we're going to sum all of these numbers, but instead of multiplying by I, we're going to choose a really large number, which I'm going to call P, and then add that to I. and then we do our mod. Okay. So P is going to be a huge number, like 1,000,000. And then when you add that to I, it's going to be unique for each one, which will eliminate the commutativity problem. And then you multiply it by the number. And then finally, when you do this mod K step, it's going to snap it to be within 0 to K minus 1. So this huge number gets pared down. And so it's, in effect, it's like having it's going to make it much more random than before. It's not perfect, though. It won't be a completely uniform distribution. And we talked about uniform distribution in the in our previous series on random numbers. But it'll be a lot better. So that brings us to some of the drawbacks of hash tables. Hash tables are great because they let you look up these values really quickly. But you have to always be thinking about what hash algorithm you use. The more expensive your hash algorithm, then the less likely you are to have collisions. But then it's more expensive, so the slower it will be to look up your data when you need it. Collisions, of course, we went over before, are a problem, and you have to have a strategy for how to deal with them. And I am including in the description of this video a link to the Wikipedia article on hash tables that has a lot of strategies on how to deal with collisions. So if you're interested, go and read that. It's really interesting. There's also the problem of empty space. Let's section this off here. The larger your hash table is, the less likely you are to encounter collisions, but then you'll have a lot more empty space. So you have to know how much data you plan to store in your hash table, so that you can minimize the amount of. So if you know you're only going to have 100 items in your hash table, you're not going to make a hash table that is this size 100,000 or something like that. Deletes are a problem because suppose we delete bat and then we go to look up Firefly. I think I mentioned this already in the video. Then there will be no object here, and so the algorithm will say, oh, there's no object here. Well, we'll just put Firefly right there, and then we'll have Firefly in 2 places. So deletes can be a problem. There are algorithms to deal with them, though, and again, go to that Wikipedia article, and it will list a lot of the algorithms. And finally, hash tables are sort of inflexible in that you can't change the keys or the size of the hash table. Neither one of these can be changed. If you change the size of the hash table, then you're changing the hashing algorithm, and so everything will have to be put in a different place. And if you're changing the keys, then you're changing, again, these are the keys right here. And so you're changing the location of the thing that you're storing. And so, for example, if instead of a fish, you want to say it's an anglerfish. Is an anglerfish an actual fish? I think so. Then your item would be stored in a different place, which means that it wouldn't be able to find it, even though all we've done is changed the name. Like if I go to the courthouse and tell them I'm changing my name from George to Paul, that doesn't change any of my properties, okay? People should still be able to find me and learn things about me just because I changed my name. But with a hash table, it's not possible. If you change the fish to anglerfish, then the hash algorithm will point anglerfish to be somewhere else in the array. This is anglerfish. And then all the data for fish will be lost. So I think that's the end of this video, and we're going to continue next week with more optimization techniques. And I think we'll finally be getting away from algorithms and into, not algorithms. See you then.